Good morning, good noon, and good evening, all of you, and welcome in the session of this workshop. And today is sixth day of this ongoing workshop on numerical methods and its applications in physical science and engineering. Today in the session, Dr. Harshad R. Patel will be speaker. He has joined the Sardar Vallabhbhai Patel Institute of Technology, Vasad, Gujarat, as an assistant professor in applied science and humanities. Since September 2008, with an academic career spanning over 13 hours, Dr. Patel has taught a number of subjects ranging from the first year to master level in mathematics. He also delivered more than 27 expert talks at various colleges and universities. He has published more than 28 research papers in UGC and Scopus, indexed international journal, and more than 10 research papers presented in international and national conferences. Also, he has jointly published 4 books in mathematics and slowly 2 international research level book in MHD flow published. In addition to that, Dr. Patel has organized more than 9 FDP, STTP, workshop, conference, seminar, and attended more than 33 seminar workshop, STTP at national and universities level. He is also associated with various professional bodies of mathematics and review more than 50 research papers. Under his supervision, 4 students have continued their research work for PhD degree. I hope his expertise in this area will be very helpful, informative, and valuable to all the participants. Dear Professor, welcome in this session. Now, I think you can share your screen.
Okay, sir. Thank you.
Yeah.
Okay. Now visible my screen?
Yes, sir. Your screen is visible to us.
Okay. Okay, now we start.
Yes.
Hello.
Yes, sir. Visible.
Okay. Sir, my voice is audible?
Perfect.
Okay. Okay. First of all, thank you. Thank you, sir. Thank you very much for giving best opportunity. And now we start our today's session. So the today's session, the topic is how to solve the partial differential equation using the MATLAB software. So basically, first we discuss about what is the partial differential equation, how to find the solution using the different types of the method. So the partial differential equation is an equation that involves an unknown function and its partial derivatives. As for example, if we write del square u upon del x square is equal to del u by del t, where u is a function of x and t. So there are 2 independent variables. So we call this is the partial differential equation. So PDEs involves 2 or more independent variables. Now, basically, so a PDE is a linear if it is a linear in the unknown function and its derivative. As for example, This both example are a linear partial differential equation, and the remaining three example is a non-linear partial differential equation. So the application of the MATLAB, we solve this type of PDE, which is a linear and the non-linear. Now, the next is a classification of PDE. So linear second order PDE are important set of equations that are used to model many systems in many different fields of science and engineering. The important why? Because each category specific engineering problem, like a fluid flow problem, the another MHD flow problem. There are different types of the fluid flow problem which is arise the mathematical modeling which is convert in a system of partial differential equation with the initial and the boundary condition. Now, how to classify the PDE? Actually, we know that if the second order linear partial differential equation, which form is A into UXX plus B into UXY plus C into UYY plus D equal to 0, where A, B, C are the function of X and Y, and D is a function of X, Y, U, UX, and UY. Now we check the nature of the PD, then we find the value B square minus 4AC. And there are three categories. If the B square minus 4AC is a less than 0, then we call the given PD is a elliptic. If B square minus 4AC equal to 0, then the given PD is a parabolic, and B square minus 4AC is greater than 0, then we say that the given PD is a hyperbolic. So if we want to find the nature of the PD, then first we find the B square minus 4AC, and using three cases, we check the given PD is a which type, elliptic, parabolic, or hyperbolic. Now some basic equations which is arise mostly in a partial differential equation or system of partial differential equation. So the first is a Navier-Stokes equation. It is elliptically in a space and parabolic in a time. Laplace and the Poisson equation, which is both are elliptic. And most of the fluid flow problem have a non-linear terms called the advection term in a momentum and energy equation respectively. Now, this is some basic concept about the partial differential equation, because we start the solution of the partial differential equation using the MATLAB software. So obviously, first we know that which type of the PD we solve using the different types of the method. So there are different types of the discretization method. The first is a finite difference method, the finite element method, finite volume method. So all the three method is very, very important for discretization of the given any real world problem whose boundary is something unknown and also known. And the next is a spectral method. So all are the method can be used for finding the solution of the partial differential equation. So the finite difference, finite element, and the finite volume method is very, very important in engineering field. Now, we know that there are different types of the boundary condition is there. The first boundary condition is a Dirichlet condition, Newman condition, and the mixed boundary condition. In a Dirichlet condition, only the simple function. In a Newman condition is the derivative is there. And in a mixed boundary condition is one term is the Dirichlet term and the another is the Neumann term. Okay, so this is the mixed boundary condition. Now, the first our today main session, the partial differential equation in a one space dimension. So basically, the initial boundary value partial differential equation with time t and a single variable x, MATLAB has built in a solver which is called a PDEPE. So this solver is very important for solving any partial differential equation which is the form is C x p u ux and ut, where C is a function of x, t, u and ux with the derivative ut is equal to x raised to minus n del by del x in the bracket x raised to m. Now b is a function of x, t, u, ux. And the another source term s is also the function of x, t, u, ux. X, L, T, U plus Q XLT into B XLT UX is equal to 0. And this another boundary condition, this is the XL. XL is represent the left end of the boundary. And XR is represent the right end point of the boundary. And this is the initial condition when t equal to 0, the function is f of x. So the whole this form where we use the inbuilt solver which is called a PDEPE. So again I repeat, so the any differential equation whose form is sometimes in a left side the derivative is a ut and the coefficient we call c. The c is nothing but a function of x, t, u or ux. In the right side, b is also a function of x, t, u and ux, and s is a source term. Now both are boundary condition where this condition is based on the left end and this is the for right end. So both are the boundary condition and this is the initial condition. So the total problem which is arrives in a partial differential equation with a boundary condition and the initial condition. But the form is especially this type of form, then we use the PDEP. Inbuilt solver we use when this type of form is given. Otherwise, we can't apply the PDEP solver. Now, is observed that the same function b in this form b is appear in both equation and the boundary conditions. For clarity, each set of the function will be specified in a separate M file. That means what? When we start the write to the program, then first we write the function file for C, for B. Okay, so we find, we separate M file, that is the function C, B and S associated with the equation should be specified in a 1M file. The function P and associated with the boundary condition in a 2nd M file. Again, keep in mind that B is the same and only needs to be a specified once. And finally, the initial function fx in a 3rd. So the command PDEP will be combine these M file and return the solution of the problem. So we consider this inbuilt solver PDEP. So this is the 3 required M file. First for CBS, second for P and Q, and third for the initial condition. Now we discuss specially some example how to solve the partial differential equation using the PDEP software. So suppose we consider one-dimensional heat equation with the initial and boundary condition. We start with the simple problem. So we know that the one-dimension heat equation is a UT is equal to UXX. The boundary condition x is equal to 0 is equal to 0 and x is equal to 1, we consider u equal to 1. And the initial condition ux0 is equal to x. Now we know that one dimension heat equation, that means suppose we consider the figure. This is the one of the figure where x is nothing but the space and t is a time. When x is equal to 0 is indicate the left hand and x is equal to 1 is the indicate for right hand. So the indirectly the length of this region is 1. Now what is the initial condition? So initial condition is when t equal to 0, this is called the initial condition. We consider ux0 is the function of x. We consider simple x. So now one of the problem which is a heat equation, one dimension heat equation, which the initial condition as well as the boundary condition. Now we solve this problem using the PDEPE solver. Then first we compare this equation as well as the boundary condition and the initial condition with the standard form, because it is required for finding the value of C, value of B, and value of S. Also, it is required for the this boundary condition XL and XR. XL is the left hand point and XR is the right hand point. So how to decide? So suppose in our problem, in our example, the C is nothing but our example UT is equal to UXX. UT is equal to UXX is our partial derivative. So the form is nothing but C into UT. The standard form is a C into UT. That means UT coefficient is in this example is constant 1. Therefore, we write C equal to 1. So in that case, the function C xtux we call 1. Now what is B? So B, that means we know that this is the second order derivative, but our form is a del by del x into x raised to m b. B is also function of x t u ux. So in that case, the ux is our b. So we write b is nothing but ux. Now another term here, the source term is 0. So s is nothing but 0. So any example is given, which is the form is this form, this type of form. So we write the program, then first we decide the value of C, value of B, and value of S. After deciding the value of C, B, and S, which is we specify the function M file. Suppose equation1.m. This is the different things. Okay, we write the name is not perfectly equation1.m. We choose any. The specification, what is m? M is equal to 0. M is equal to 0 we consider because here m is x raised to minus m. So if we consider m is equal to 0, that means there are no symmetricity. If we consider m is equal to 1, m is equal to 2, then the different types of the nature is there. We discuss later. Okay. So first we define the function CBS, and for that this example particularly here we write equation1 x t u du dx. Equation 1 is nothing but the MATLAB function m file that specifies a PD in time and one space dimension. Okay, so C equal to 1, B equal to actually ux, but in a program we write du dx. Du dx. U is a dependent variable, x is an independent variable. So we write ux is nothing but du dx, and source term will be. So again, I repeat, ut is equal to uxx. So the coefficient c equal to 1, the b equal to ux, but in a programming we write du dx, and the last source term will be 0. Now for our boundary condition, how to write. So P and Q, now this first will be used for the left hand, and second can be used for the right hand. So we know that when P is a function of x, t, and u, but in the left hand we know that x is equal to 0. So here we write P, x is equal to 0, t and u, we get u. Why we write u? Because our boundary condition for this particular example, only when x is equal to 0, then the u is a 0. U is nothing but the temperature because the equation is a heat equation. Okay. Now for that case, when x is equal to 1, that means right hand. So how to write the boundary condition? We write in the form equal to 0. So in this case, we write u minus 1. Here we write u minus 0. Okay. So u, when t equal to 0, boundary is also 0. So we write u minus 0 is nothing but u. In this case, we write u minus 1. As suppose our our another boundary condition ut 0 is suppose 5. So how to write u minus 5, u minus 5. If here another function, then u minus the function. So now the boundary condition, when t equal to 0, so the only value u, and t equal to 1, then we write u minus 1. Now, and here q for t equal to 0, here there are no derivative, so we write equal to 0. This is also equal to 0 because our form is a p, where p is a function of xl, t and u, but is a q is xl and t, but b is a function of the derivative. So suppose our boundary condition is an Newman condition or the mixed condition, then b is not equal to 0. But in this particular example, there are no derivatives. Simple boundary condition. In that case, p is used, q is nothing but 0. So q is equal to 0 for both case when left hand and the right hand. Now we define the function file for the boundary condition. In the first case, we define the function file for the CBS. Second, function file for the boundary condition. So the function is a PL, PR, and QR. This is the standard notation. PL is a left hand, QL is also left hand, PR for right hand, and QR is also right hand. So PL we write UL because we know that when t equal to 0 is given that u only. So in programming we write PL is nothing but UL. QL is 0. Now PR. So PR is nothing but you are right minus 1. So you are minus 1. And QR is 0. Okay. So in the programming, we write this form PL is a UL, QL is a 0, PR is a UR minus 1, and QR is 0. Then the next, how to write the initial condition. So suppose our function f of x is x, which we specify the third M file. Now the name for particular example is the initial 1.m. So the function value is the initial 1 of x and the value is x. So this is the third function file. Now we are finally ready to solve the PDE with the PDE solver PDEPE. In the following script M file, we choose a grid of x and t values. Now solve the PDE and create a surface plot of its solution. Okay, so now, okay. Now everyone visible?
Yes, sir. You are visible.
Okay. Now this MATLAB file is visible?
No, sir. MATLAB not visible. Only your presentation.
Okay. So MATLAB file is not visible. Okay.
Yes.
Okay, just 1 minute. Now MATLAB file is visible, sir?
Yes, sir. It is fine.
Okay, okay, thank you. Okay, now this is basically the PDE solver, how to write. So here we write m is equal to 0 because this is a simple problem. There are no symmetry. Now, first we know that our function u, that means the dependent variable u, which is depends on x and t. X is indicate the space and t is indicate the time. So first, obviously, this is the discretization method because the PDE basically the finite element method, which is a inbuilt solver. So obviously, discretization is required. So we consider the x discretization and t is also discretization. So we write x is equal to length space 0, 1, 20. That means we start with the x is equal to 0, our length is 1, so 0 to 1. This value x is 0 is the left hand and x is 1, this is the right hand. Now t is also we consider for this particular example when t equal to 0, 0 to 2, and we divide the interval 0 to 1. Suppose for that case, we consider simple 20, and for time, we consider the 10. That means we discretize with the x 0 to 1, with the 20 to with the 10. Now, our main function u is nothing but PDEP m at the rate equation 1. That means equation 1, initial condition, boundary condition, all are three a function. We separate all the function file and also we include only the one programming, and we include here only one programming. So we write the at the rate equation 1, at the rate initial condition for 1, and at the rate boundary condition 1, and our independent variable is x and t. Now, our first function is nothing but we discuss CBS. So CBS is equation 1, x, t, u, and du dx. A function for the independent variable x, t, u, and du dx. So, for particular example, we consider c equal to 1. We discuss in a PPT. So here we write c equal to 1. Now b is du dx. And the source term for particular example, s is equal to 0. So now this is the one function file. We also define in a separate m file, but we write only only one programming. We include all the function file in only one m file. So also we write in that case. Okay, now the first is completed. This is the CBS. Now second is the initial condition. So another function we write value, and this is equal to the initial one is the name of x, because the initial condition is depends only on x, and we consider value is x squared. Okay, in PPT we consider x, no issue, but in this example we consider x squared. So the first is the CBS, second is the initial condition, now third is the boundary condition. So we discuss obviously in the PPT PL, QL, PR, and QR. So PL is the left end, PR is the right hand without derivative, Q is the boundary condition for the left hand and right hand, but in QL and QR, which is include the, I think, Newman boundary condition, which is depends on the derivative. Now, for that case, we consider BC1 is the name for the function file, XL, UL, XR, UR, and the independent variable T. Okay. So PL, our first boundary condition is PL is only UL. Why? Because U0T is equal to 0. Now there are no derivatives, so QL is 0. The another boundary condition is the right hand is the U 1T is nothing but 1, so U minus 1. So we write UR minus 1. Because this is in R is indicate the right hand and there are no derivatives, so QR equal to 0. So the initial and boundary condition of the heat equation, this is required. First we discretize, we consider X, we consider T. Now this is the standard form for the inbuilt function PDE solver. @equation 1. Equation 1 is nothing but the first function file. Initial 1 is the second function file. And BC1 is the boundary condition third function file. So all the function file we define separately. Okay. And then we write the program U is a PDEP M @equation 1 initial 1 boundary condition 1 X and T. Now we run the program, then just 1 minute. Actually, the compiling is start. Actually, this is the some time taken for the calculation. Okay, the program is completely done and we get the figure. Okay. Now, this is the solution. U is the temperature. We discretize with X and T. X is 0 to 1 and we discretize them up to 20. So 1 to 6, 7 to 12, 13 to 18, and 90, 20. Now the row is indicate the value of X and the column is indicate the value of T. So this is the solution of the heat equation with initial and boundary condition. So this value is nothing but when x is 0, t is 0. This value is nothing but t equal to 0, and I think 1 by 20, x is 1 by 20. This value is nothing but t equal to 0, but x is a 2 by 20. This value is nothing but x is t equal to 0, 3 by 20. So if we want to find the temperature for the different point, then we use this type of the discretization, and we get the temperature value for all the point. And also we draw the graph. This is the 3D graph. So this is the totally 3D graph, and we get directly the solution as well as the, suppose we find the 2D graph as well as the 3D.
Dear participant, if you have any question related to this program, please feel free to ask. You are permitted to unmute. You can unmute and put your question.
Hello.
Yes, sir. We are waiting if anyone have question.
Okay. Okay.
Yeah.
No issue.
Yes. Yes. I think there is no question, sir. Two participants replied in the chat box. There is no question.
Okay, sir. Now I continue. Yes, sir. I continue.
Yes, sir. Yes, sir. Please continue.
Okay. 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 Now.
Yes, sir. Continue.
Okay. Okay. Thank you. Now. This is the program we discussed in earlier as well as in MATLAB. Now, what is m is equal to 0? There is a no symmetry in our problem. So taking m is equal to 1 is specifies the cylindrical symmetry, and if we consider m is equal to 2 is for the spherical symmetry. So in our case, there are no symmetry, so we write in a program for m equal to 0. If we write m equal to 1, so this is indicate the cylindrical symmetry. M equal to 2 is indicate the spherical symmetry. So this is our program. Already we discussed. Okay. Now the next, this is the first example is very simple. Now we discuss the system of the partial differential equation, how to solve. So consider the one system of the partial differential equation. The first equation is a u1t, u1xx plus u1 minus u1 minus u2. Okay. Now one question is how can apply this method in solving a couple of non-linear differential equation. Okay. Now the second example is based on the non-linear system of the partial differential equation. How to apply we discuss here. So the first equation is a u1t is a u1xx plus u1 1 minus u1 minus u2. The second equation is a u2t is a u2xx plus u2 1 minus u1 minus u2. So this is the couple of the system of partial differential equation, system of partial differential equation as well as this equation is not a linear. This is the non-linear. Okay. The boundary condition when x is equal to 0, then the first u1x is 0. U2 is a t comma 0. This is the boundary condition. U1 T1 is equal to 1 and U2x T1 is also 0. So both are the U1x and U2x means the partial derivative with respect to x. That means our Newman condition as well as the Dirichlet condition. Now the first initial condition is x squared and for the second x into x minus 2. So the whole problem is the non-dimensional form of the PD model for two computing the population as with the solving the OD in a MATLAB. The basic syntax for solving system is the same as for the solving the single equation. The procedure is similar. In a first, in only one equation, we find C, we find B, we find S. Similar procedure for the system of the PDE. We also find C, we find B, we find S. Also initial condition and function file for all the three cases. So where each scalar is simply replaced by the vector. Because only one value, then obviously this is the scalar, but suppose more than one, then we use the vector form. We use also the matrix vector form. So in a particular, the MATLAB specify a system in a PD. Okay, now how to solve this system? So first we discuss the form. So similar form, but only one equation, so we use only this. But if more than one equation, then we write this is the C1, this is the B1, this is the S1. Now second is the C2, B2 and S2. Up to and so on, the n time equation, so Cn, Bn and Sn. Similarly, the boundary condition for P1, Q1, P1 for right hand, this is the left hand, right hand. So both are the condition for the first, then P2, Q2 for XL, XR up to and so on. So if we use only one equation, then only directly we write the CBS, but is more than one equation, then the procedure is similar, but obviously this is not a scalar form, this is the vector. So now next is the initial condition. Obviously we write the function f1, f2 up to fn. So in our example, we have what is C, what is B and what is S. So this is the vector form. We write C1 value, C2 value. So in our example, the U1t, the coefficient of U1t is a C. So here coefficient of U1t is 1, U2t is also 1. That means the C is nothing but the vector form is 1, 1. C is nothing but the vector form 1, 1. So here we write C1 is a 1, C2 is also 1. Now what is B? So B, that means U1x, U2x. And our form is del by del x. So obviously the B1 is nothing but ux, B2 is a ux. So in that case, B1 and B2 is a U1x and U2x. Now S is a source term, a remaining term. So how to write S1? So in that case, S1, this the whole term is a S1. This is also the whole term is a S2. So both are the source term, remaining term. Here C, here B, and the last one is a S. So S is nothing but U1 in the bracket 1 minus U1 minus U2, U2 into 1 minus U1 minus U2. Okay. So first we decide the value of C, but in a vector form, value of B, and value of S. Okay. Any
Excuse
question?
me, doctor. Yes, I have a question, sir.
Yeah.
Can you
Hello.
go back to the previous slide?
Yeah. Okay.
Yes. Here we are taking the double derivative of uxx.
Yeah.
But if there is u triple x, third derivative is here. So what will be the value of b1 and b2?
But in a third derivative, because here only we use the for uxx. Because suppose here we write uxx, then we use, but the b1 is nothing but the function of only u and ux. So this is the specially case
Other
for the
derivative.
second order derivative.
But if it is third order derivative, what will happen?
Hello.
Yes, doctor.
Okay.
I am saying, but if there is third order derivative in the space variable, then what will be the value of b?
Actually, we can't consider the third order derivative because here b is a function of only u and ux. Only the first order derivative. Because in a MATLAB programming, if we write ux as is nothing but del square u by del x square, but in a PDEP solver, we can't write the form. Actually, only one first order derivative, then we write du dx. So
Okay.
this form is used for only the first order derivative. That means the second order up to, because here del by del x is there. So ux is there, then obviously this is the second order. But if our PD is the third order, use the this form PDP, because we can't
cannot use
find the value of
PDE.
B1 and B2. Huh?
We cannot use this PDE.
This yeah. This inbuilt function in we can't apply for the third order derivative.
Okay, doctor. Thank you.
Okay. Now continue.
Yes, sir.
Okay. Okay. Now our C is obviously 1, 1. The coefficient B is U1x, U2x, and S is the source term. Okay. Now, similar procedure. So the first is a function file CBS. We write equation to x t u du dx. So for C, we know that the coefficient of the left hand side, which is a partial derivative with respect
Sir, you are not audible. Sir, please check your audio.
u1 minus u2. Then u2 star 1 minus u1 minus u2. So this is the vector form for source term. This is for B and this is for C. Now boundary condition. So the boundary condition, the P is nothing but for left end. So when x is equal to 0, x is equal to 0, then what is the value of P1? P1 is 0. Because in a condition, x is equal to 0, there are no boundary condition is given. U1 is given, but when x is equal to 1, that means right end value is given, left end boundary condition is not given, so obviously we write 0. So P1 is 0. Now what is P2? So the condition is given U just okay, U2 P0. That means when x is 0, then U2 is given 0. The value is given. U1 is not given. That means we write directly 0. But U2 is given, so we write U2 minus 0. So U2 minus 0, obviously we write U2. Okay. Now in a right end, the condition is U1. When x is 1, the value is 1. So how to write in the programming U1 minus 1? So for that case, we write U1 minus 1. And P2, that means the boundary condition when x is 1, for P2, this is equal to 0 because not given. So when x is 0, when x is 1. Now, the derivative is also given. So x is equal to 0. What is the Q1? So Q1 is nothing but here condition is U1x. U1x, when x is 0, the value is 0. And U2x, when x is 1, the value is 0. So how to write? The derivative condition is given, but the value is 0. So we write 1. So Q1 is 1. What is Q2? Q2 is 0. Now when x is 1, so again the Q1 is 0 because not given. And Q2 is given that something value. The value is 0, so no issue, but we write 1. So all are the boundary condition. Now, how to write? So PL, that means the left end without derivative. So obviously 0, and the value is here not given, so we write 0, and here value is 0, so we write U12. QL, that means the derivative. Value is 0, but derivative is given the first order. So we write 1 and then 0. Similarly, PR is a UR1 minus 1 and 0. And QR is 0 and 1. So if the system of PD is given, then we write in a vector form. Now, what is the initial condition? So for the first case, the initial condition is, and the second initial condition is x minus 2. So obviously we define the function file, and we write the first vector, first value is x squared, and second value is x star x minus 2. So what is the program? m is equal to 0, so there are no symmetry. X is equal to, we divide the interval 0 to t is we divide the interval 0 to 1 in a 10 part. Okay, now similar we discuss in a MATLAB. Okay, so first we write the program m is equal to 0. First we write m is equal to 0. Okay, now next we write x is equal to the linspace 0 to 1. We divide the 20 parts. Now t is the time, we divide the 10 parts. Okay, then the solution similar, m first function, second boundary condition, x and t. Here there are two solutions because this is the system of PD. So U1 is indicate the first solution, U2 is indicate the second solution. Now we draw the graph for U1. So surf xt U1 and the second surf xt U2. Okay. Now what is the first function? CBS. The name is equation 1. Now we know that C is left hand is 1, 1. B is also 1, 1 into du dx. And the source term, the first term is a u1 into 1 minus u1 minus u2. And the second term. So this one is the function file for CBS. Now the second is the function file for the initial condition. We know that there are two function u1 and u2 for the particular, the initial condition is x squared and x into x minus 2. Now third is function file for the boundary condition. So PL obviously 0 and U12. QL we write 1, 0. PR is a UR1 minus 1 and 0. And QR is 0, 1. So there are three functions. We discretize them and we write the PDE PE solver. Now we run the program. Okay, we get the first solution u1xt and second u2xt. Now, how to indicate the solution? So obviously, this is a u1, एक्सपर्ट लेक्चर चालू दो कलर हेलो हेलो
Yes, sir.
okay
Yeah,
my voice is okay clear
yeah.
okay
Dear
okay now
participant, if you have question, please ask from the speaker. I request to all the participants to ask any question if you have.
any question
Hello, sir.
yeah
Good afternoon, sir.
hello
Hello, sir. Can you hear me, sir?
yeah
Okay. Thank you so much for the presentation.
okay
Please, I want to know, will it be possible to solve a problem that is nonlinear and coupled, then
yeah
before coming up with a program on MATLAB to be able to get the numerical solution? That is it possible to solve a problem that is nonlinear and coupled analytically, and then now come up with a code to get a numerical solution for the analytical form with this method?
Actually, if the problem is a system of partial differential equation and non-linear, so the analytically solution is finding very difficult. So in that case, we use different types of the method, which is not analytically, but this is the semi-analytical method and numerical method.
Okay.
So I think the semi-analytic methods, I think is the homotopy analysis method.
Okay.
So the homotopy analysis method can be used for finding the non-linear, highly non-linear partial differential equation with the initial and boundary condition, whose solution is analytically not possible. So in that case, we use the short form is a HAM. HAM, that means the homotopy analysis method. And we find the analytic type of the solution. Because the solution of the form is the series form.
Yes, yes.
And
that's
the form is a series form. If the
that's
series form, then this is not. Yeah.
Okay.
So
now,
okay, there are different types of the software is there. I think the Mathematica is there. So in Mathematica software, we use different programming. The is also there for finding the highly nonlinear PD.
Okay. Thank you, sir. What actually happened is this. I think in some cases, it's also possible to convert these PDEs to ODEs. Is that possible, sir?
If any real world problem we convert in a mathematics. So suppose our most of the problem, which is a fluid flow problem, we convert in mathematics. Then this is the dimension with the dimension problem. We use the similarity transformation
method.
Then so then we convert in a non-dimensional parameter, non-dimensional system of PD. And we convert the PD to the OD. Hello.
Hello, sir. Yes, sir. I can hear you. Hello, sir.
Yeah. Hello.
Yeah. I can hear. Hello, yes, sir. I can hear you, sir. Hello, sir. I can hear you, sir.
Okay.
I can hear you, sir.
Okay.
Hello,
So
sir.
your question is how to convert the PD to the OD.
Actually,
Yeah?
yes, I have been able. Yes, I have been able to convert it.
Okay.
I've been able to
So
convert it from PDE to ODE, highly nonlinear and coupled. But the problem now is how to use the homotopy analysis method to resolve it
okay.
before I can now apply mathematical.
Actually, the homotopy analysis method is nothing but the series of solution. But in that case, if the problem is a highly non-linear, so the HAM can be used for the separate the non-linear term.
Yes. Okay.
If any equation is there, then there are two terms, obviously. The one term is a
yes.
non-linear term, the another term is the linear term.
Linear, exactly.
Yeah. So the HAM can first the separate both. Then obviously we initially we consider suppose the solution of this given problem is like this type. That means the initial condition which is satisfied. We suppose auxiliary parameter and also initial guess. Because suppose our boundary condition is 1. ux0 is 1. Sorry, u0 t is 1. That consider the any function which initially satisfied the boundary condition, and then the HAM can be used for deform the initial to the final solution.
Okay.
Okay. So initially we decide the simple auxiliary parameter as well as the initial parameter as well as the linear part and the non-linear part, and then we separate, and there are big procedure. Okay, and then we get the solution.
Okay.
But basically HAM can be used for the highly non-linear PD. So this is very important because obviously the fluid flow problem is not a simple problem. This is very highly nonlinear problem, and
Yes.
how to solve this is important.
Yes. Yes, sir.
Okay. Okay.
Okay. Thank you, sir. Maybe before the end of the, I would like to
now
get
I continue.
your address.
Okay, I continue. Now in both type of the problem which is we discuss, both type of the example we discuss. The first is the simple one example, and the second is the system of PD with the non-linear term. Okay, now we consider the one research problem, how to apply the this PDP inbuilt function. So suppose our problem is fluid flow, micropolar fluid flow. Okay, just 1 minute. Okay, the problem is effect of the magnetic field on unsteady natural convective flow of a micropolar fluid between two vertical walls. That means suppose our problem, what is the free convective? There are different types of the form. Unsteady, that means del u by del t is change. Then we call the unsteady. Natural convective, so free convective, forced convective, and mixed convective. Okay, so this is the one of the real world problem. When the fluid is a flow, suppose this is a fluid is a flow in this direction, and this is a plate, two vertical plate. Now in that case, the left hand is y equal to 0, and the right hand is y is equal to L. We apply the magnetic field in right here, and we develop the mathematical modeling of this problem. The problem is fluid flow problem between two vertical walls. So the mathematical formulation of this problem is nothing but there are three equations is required. The first, when the fluid is flow, then the momentum is obviously important, because without the momentum, without the velocity, the flow is not considering. So obviously the momentum equation is the first equation. Now the second equation is the energy equation. The energy equation is nothing but the heat transfer equation. So in a fluid flow problem, the fluid equation, that means the momentum equation, energy equation, and suppose we consider the mass transfer also, then the third equation is the concentration equation. So basically, fluid flow problem with the heat and mass transfer is momentum, then the energy and the concentration equation. So we develop this problem in mathematical form. So the mathematical form is equation 1, 2, 3. Now equation 1, 2, 3 is the dimensional form with initial condition is 4. We consider the initial condition for only the length of 0 to 1. So y is value of 0 to 1. Now left and the boundary condition is this is the right hand boundary condition. Okay. Now using the similarity transformation, the given equation will be converted in a dimension form. Dimensional form. So we get the equation number 8, equation number 9, and equation number 10, and equation number 11. Now equation number 8 is nothing but the momentum equation. Equation number 9 is angular momentum equation. Also we call the micro rotation. The equation number 10 is the energy equation, and equation number 11 is the concentration equation. That means the heat mass transfer. This one is the heat transfer, this one is the mass transfer, this is the micro rotation, and this one is the momentum equation. Now in a motionless approximation, if we consider the heat transfer and the mass transfer, what is the effect in the fluid flow? So this value is indicate the magnetic field effect. Okay, now this is the real world problem which is a micropolar fluid is flow between two vertical wall. Also we consider the heat transfer and the mass transfer. Now the boundary condition when t equal to 0, the u equal to, that means the velocity, micro rotation, then temperature and the concentration will be 0, where all the value of 0 to 1. Now for t greater than 0, that means the left hand, we consider u equal to velocity will be 0, micro rotation is also 0, but the temperature and the concentration is 1. Now in a third one, when y equal to 1, u and w, value of velocity and micro rotation we consider 0, but theta is we considered constant m, and concentration we consider another m. Okay, now the whole problem is a system of PD with initial and boundary condition. So now this equation system of PD we solve analytically, but this is a difficult. So we use numerical method for finding the solution. So in that case, first we check the equation number 8, 9, 10, and 11 all and order partial derivative. Okay.
and the form is a simpler, not a non-linear form, so no issue. And this is the fit for our PDE so inbuilt solver. So in this particular example, we apply directly PDE PE solver. So now how to apply? Okay. So now first we write similar procedure. First we write the function PDE x4, m is equal to 0, x is 0 to 1 because our fluid problem is arising in two vertical walls. So left hand is x is 0 and right hand is x is 1. Now we consider time t is 0 to 2. We divide the interval 0 to 1 with 32 and 0 to 2 with 21. Now obviously this is the similar procedure. So first U1 the first solution, U2 for the second solution, U3 for the third solution. The first in this program actually we consider only the three equation. Concentration is not included in this program, but if we include, then we write U4 solution of 4. Now we draw the graph 1, 2, 3. So this program is nothing but the same program, but only concentration is not included. The first U1 is indicate the velocity, U2 is indicate the micro rotation, and U3 is indicate the heat transfer or temperature. Okay. Now function file. So obviously CFS. So in our program, here indicate del U by del T, the coefficient is 1. Del W by del T coefficient is 1. Del theta by del T, sorry, the printing mistake. Okay. Okay, del theta by del T is coefficient is 1. This equation for programming particular, we not consider, only three equation will be considered. So what is the value of C? Is 1, 1 and 1. So C is nothing but 1, 1 and 1. Now for simplicity we write all the physical parameter constant value. R is also constant value, GR is also constant, GM is constant, R is constant, M is constant. So we define the all PR is constant, R is constant, M is constant, B is constant. So all are the constant value. Also 1 plus R we write 1 plus VP. 1 plus 0.5 into R. In this value we consider VPP1. This value is a VPP. This value we consider VPP1, and the coefficient of this is a 1 plus NR upon PR. So 1 plus NR upon PR is okay, 1 plus NR upon PR. Here we write 1 plus NR upon PR, where NR is suppose something 2. Okay. So VPP, this is constant. VPP1 is also constant. Y is 1 plus NR upon PR is also constant. So 1 plus R constant. This is also constant. This is also constant. And we know that the coefficient of del square u by del y square, del square w by del y square, del square theta by del y square. So the first coefficient is a VPP, 1 plus R. 1 VPP1. And third coefficient is a Y. All the coefficient we write in a vector form. Now into du dx, into du dx. So the whole term we write VPP, VPP1 and Y vector into du dx. Plus, now here the first derivative is also that. Here also, and in a third equation not include the first order derivative. So how to write this term? So this term is nothing but we write R into the first order derivative. First order derivative we write u2 because f is already by del x into something. So first order derivative we can't write du dx. Second order derivative we write du dx. But all the term which is a first order derivative coefficient, so VP u2 because u1 is nothing but the first equation, u2 for second, u3 for third. So u1 is nothing but u, u2 is nothing but w, and u3 is nothing but theta. So in the first equation, R into the derivative of del W by del Y. So we write R into R is a VP into U2. Second, minus R into B into del U by del Y. So the second is a minus R into B into the derivative, but with respect to u1. And third, there are no extra term derivative, so we write 0. So how to write this term? First we write all the form, then this one and this one. So we get this. Now the source term is gr theta gmc minus m square u. This is the source term for first equation. Minus rb into 2w is the source term for the second equation. So we consider some assumption. Y1 is a u3. U3. What is u3? So gr theta. So u3 minus m square u1, because this term is not included in our problem. So g theta where u3 minus m square u1. Y2 so is minus rb into 2w. So minus 2 vp mp into u2. So what is the source term? The first is a y1, second is a y2. Third, there are no term. So third is a 0. So this is the source term. Now the initial condition initial condition is all are 0. T equal to 0, then u0, w0, theta 0. So we write 0, 0 and 0. Okay. Now the last is the boundary condition. So also the boundary condition when y equal to 0, u is 0. So we write u11 minus 0, u12 minus 0, but theta is 1, so u13 minus 1. Now in there are no derivative, so all QL is left and 0. Now y equal to 1, when y equal to 1, then u equal to 0, w equal to 0, and theta equal to f. So u are 1, u are 2, and u are 3 minus k, that means m. K is a thermal ratio. Now QR, there are no derivative term for y equal to 1, so QR is all are 0. Okay, so this is the total our real world problem which is converted in a mathematics, which is given that the system of PD, momentum, energy, and concentration equation. Now, after define this program, okay, just 1 minute.
Sir, your voice is not audible.
Hello.
Yeah.
Hello. Yeah.
Hi. We are not hearing you. Audio.
My voice is clear. Hello.
No.
My voice is not clear. Hello.
Hello, we can hear you, sir.
Hello.
Hello, sir.
Just 1 minute. Hello.
Hello, sir.
Yeah.
We can hear you, sir.
Sir, your lecture is over now?
No, sir, just 1 minute.
Okay.
Okay, now my voice is clear?
Yes, sir, it is fine.
Okay, okay, now I continue. Okay, same problem. This is the simple system of partial differential equation. Now another problem also we discussed the thermal radiation and the chemical reaction effect on unsteady MHD gas and fluid flow past an exponentially accelerated vertical plate in a porous medium. So in a similar problem, we define the mathematical modeling and we get the momentum, energy and concentration equation with the boundary condition, and we develop the mathematical modeling of equation 10, 11 and 12 for momentum, energy and concentration with the initial and boundary condition, and we solve this problem in the MATLAB. So suppose this is our problem, and in only one program we also develop the we also develop the all the figure which is the importance in our problem, and we also define the all the figure which is different value of the parameter which is effect on velocity as well as the concentration and energy equation. I think this is the program. Now I will try to run this program. So this topic is importance for finding the different types of the solution, which is simple second order partial differential equation with the initial and boundary condition. This is the system of PD, and this is application very important. Suppose we consider the blood flow problem. This is also applicable because the blood flow is indirectly the fluid related problem. So this method is very important. Okay, now actually I stop here. Our program is, I think, continue, but some time taken, because in a one program I solve all the physical parameter. Okay, sir, I stop here. Hello.
Okay, sir. Okay, no problem. I ask to the participant if any question want to know from the
Okay.
speaker.
Any question?
Sir, just we need to see the result of this problem which you are running right
Yeah,
now.
yeah. Just 1 minute.
Okay, sir. Thank you. And your presentation was very good. And these are really very helpful programs and the information which you shared with us.
Okay. Actually, if any doubt, then also contact me. On my contact is also shared with Dr. Meher sir. So if any real world problem which is convert in a system of PD, so now this is the complete in a one click. All the graph which is this type of graph I show here. Okay, this is the concentration and the effect of the one of the parameter is the chemical reaction. So obviously this is the indicate when we increase the chemical flow, yeah, any fluid flow, particularly this example, the concentration will be decreased. Now the another this 23 figure is effect of the chemical reaction on temperature, then chemical reaction on velocity, then all the figure is also include in our problem, but only one click we define all the solution as well as the nature of the graph. So this is very important. So all the graph is ready to present here. Okay, now I stop, sir.
Okay,
Hello,
sir.
hello, sir.
Thank you.
Hello, sir.
Yeah.
Thank you so much for your presentation, sir.
Okay, thank you, thank you.
Yeah, thank you so much. Actually, I would like to get your contact, sir. Please don't be offended.
Okay, sir. So
I'll be able to communicate you for the.
I will share contact number in the WhatsApp group. So in future, if you have any question, you can directly contact to Professor.
yeah, sir. Yeah.
Yeah,
Always, always, sir.
And also, I think we add in the group so that if you have any question, you can put your question in the chat box also. Right now, I have, you are not able to put your question in the group, but shortly we will permit you to
Anytime, sir. If
yeah.
you any doubt, so please WhatsApp me. Okay, I will try my level best to solve the problem. Okay.
Yeah. Yes.
Okay, sir.
Thank
Okay,
you
now
so
I
much,
stop
sir.
here and I
Yes,
leave.
sir, you can stop.
Can I leave, sir?
Yes, sir. Yes, sir. And dear participant, tomorrow also our speaker will be Dr. Harshad Patel. He will continue his lecture. And I also inform you that due to some technical problem from his side, I was not able to send feedback form on your email address yesterday. And also today, I'm not able to send you feedback form, but it will take some time for sorting the problem. Hopefully, within 1 hour, I will provide you the feedback form for today as well as for yesterday. Okay. Tomorrow we will join the meeting at the same time. Okay. And I will ask to the speaker also to provide the content so that we can upload this content for the participant for their own.
Yeah, sir. Actually, tomorrow also I take the lecture.
Yes.
So I send both PPT after tomorrow lecture. Okay, sir.
Okay, sir. Okay. Thank you.
Okay, sir. Okay. Bye. Take care. Good night.
Thank you, sir. Thank you so much. Thank you.
Okay.
Thanks to all. And now it is time to close the session.
Thank you, sir.